Hi, for this demonstration I'm going to be showing how to integrate the NVIDIA Labs Fast Foundation Stereo model into ROS2. Just to be clear, it's this is the NVIDIA Labs Fast Foundation Stereo model. It's a neural network based model. It's similar in functionality, in purpose, to stereo image proc in ROS2, but I think it's more effective, particularly in low texture images. So I've got a repo here for demonstrating this. For this, so the setup for the demonstration is going to be, you need a stereo camera, and I'll have a stereo camera on a mobile robot, Thomas. This model requires an NVIDIA card, so for this demonstration my mobile robot does not have an NVIDIA card. However, I'll be running this on this model on a desktop computer which does have a NVIDIA card installed, and we'll be connecting them together over a Wi-Fi network. So let's I'm going to be using a Docker installed for this demonstration. Obviously you can use whatever is your preferred installation setup, but for this I'll be demonstrating Docker, using Docker. Let's just check that we have some of the basic installs set up correctly. So I'm going to check that I have an NVIDIA card. This is my NVIDIA card. I'm running CUDA 12.2. So my card is a NVIDIA RTX 2070. This is not a very modern card. It was released in 2018, I believe. So you don't need a particularly modern card, but you will need a card. So let us... probably the trickiest part of this will be, you need to make sure that you can run NVIDIA CUDA code inside a Docker container. So I'm just going to check that that works for me, and this is the most important part. And I'll get a Ubuntu up, and hopefully, yes. And so to check that we are able to run CUDA code, I'm just going to execute this command, and again we get the same result there, but we're executing it within a Docker container. This step was somewhat tricky to set up, and I found these instructions on the NVIDIA website helpful. It was somewhat long-winded, but I think it was these ones that I followed, and it did work. Okay, so I think the next step is so we say we clone this and CD into that. And I'm not going to clone it because I've already copied these weights, but I'll show you where, well, first of all I'll show you where the weights are located. So if we go back to NVIDIA website, weights and trade-off, you've got this here. So exactly what it do might depend upon your web browser, but it's probably easiest for me just to say what the end result should be. So if I come back here, this was where you would have cloned it. You're going to want to see these two files within, so that's your cloned folder, weights, and that folder name there. 20, 30, 48 separated by dashes. I think next step is, let me just pause for a second. Yes, so the next step is we need to build a Docker image to get this to work, and I'll just briefly show you what's in the Docker file. So we're going to use a ROS2 Docker base. We're going to set up Python, and we need a Jazzy bridge, TV bridge. This will install a PyTorch neural network. We installed, there are some other dependencies here. I'm going to set the Python path up. So in this Docker image, so we're setting up the neural network PyTorch. We're going to clone the Fast-FoundationStereo repo into it. I'm also going to copy the neural network weights into the image, so the neural network weights will be part of the image, and then we're going to clone my demo repository here, which has got the code to do the ROS2 Fast Foundation Stereo integration in, and I'll just show you what that code looks like. And and I've got a command here just to automatically run the node. Let's go back to the top. I'll just give you a very brief run through of the code. It's quite straightforward. So this is the node that does the integration. It subscribes to the left camera, left image, right image. These must be rectified images. We also subscribe to the camera info. This is so that we can determine the distance between the two cameras, so that we can convert a disparity map into a point cloud. So we basically do time synchronization. So we gather them, all of these topics at the same time, and make a single callback with all of it together. And the callback is called sync CB. So it receives the left and the right image and the left and the right camera information. It basically puts it onto the GPU, does a bit of padding. This is where we're throwing it through the neural network here, and this computes a disparity map. I unpad the disparity map again to get us back to the original image sizes. We then publish the disparity image, and I'm going to publish the point cloud. So the point cloud will take a disparity map, takes the left image and the right image, just the left image, and it needs the camera information in order to compute the distance between the two stereo cameras, so we can actually turn the disparity map into a point cloud. I won't go through the details of this, but there's sort of a certain amount of bit mangling going on, but it should be clear what it does in aggregate. Okay, so let's go back to the beginning, and I think it's time to build our Docker image. Okay, so I am going to assume that you have got to that step correctly. You probably need to unzip. If it arrives in your downloads folder, you may need to unzip it and then copy it here. That will depend on your browser. Anyway, let's go back and build the image. Okay. Right, I'm going to put you on pause for a moment because this can take a little while. Right, that looks like that has now finished. Probably took about 20 minutes. It might take longer on the first time that you run this because Docker may have cached certain layers, so it might take longer for you on the first run. Anyway, let's just see what we've got. Okay, image ls. Yeah, and we have a ROS2 FFS image. It's quite large. That may be mostly because of the PyTorch package. I'm experimenting with Docker, and I haven't spent a huge amount of time optimizing it, so there may be more efficient ways or better ways of going about things, but anyway, this approach works, which has got to be said for it. Okay, so the next step is we've built our image. Let's run our image. So of course this is a key step here. GPUs equals all, and I want to use host networking, and we're allowing shared memory access for ROS2. We're running it in the interactive mode. I'm not sure if I actually needed that on this run, because we are in fact this will launch FFS anyway. I personally like to dispose of my containers immediately as soon as I've finished with them. Not the image, the container. We keep the image. It takes a while to set up. So did I copy that? Let's just check that's copied. Let's go in and we'll run that. You could have run it from any directory. I didn't need to be in here. Anyway, we'll see if that works. Okay, well that looks promising. Okay, I've got Thomas. No, I haven't set up Thomas, my robot. Let's set up Thomas robot. And I am going to, I'll set up a new window just so we can see what's going on. Let's go here. What do I want? I'm just going to bring up a general ROS2 container. ROS2 topic. Okay, so to get nav2 to work, we need to be publishing, sorry, not nav2, FFS, Fast Foundation Stereo to work. We need to be publishing the rectified left image, the rectified right image, and we need to publish left camera info and right camera info. And if you have those 4 topics published, published, then it will, the FFS node will publish a disparity map and a point cloud. So currently, so we should have our robot is publishing our stereo images. So we need to publish that information. I'm not going to go through all of the details because I've done that in a previous video, but I've got a Docker image here which will set up my stereo pipeline. So let's get that. I'll just exit from this. So if I run that, and I am going to use, no, that's fine, that is absolutely fine. Did I want to do that? Have I got the right one? Set up the stereo pipeline. Yes, that looks right. Okay, so I'm going to split the window. So we should have everything that we need. We're now publishing the rectified images. So for the details of how to set that up, you could look at my previous YouTube video on setting up a stereo camera. I think the next thing to do is let's bring up ROS2 so we can actually see what's going on. ROS2. Okay, so we should have a disparity map. Let's see what we have here. And here we go. Here is our disparity map. Back. Hello. Okay, and we should also have a point cloud. Let's bring up a point cloud. FFS points to point cloud. Let's bring that up. And I can't see anything because my fixed frame is in map. If I put that from the robot's perspective, that should now work. I am going to change the size things, and let's just look at that from a more convenient perspective. Let's go over here. Okay, so if I go back, there we go. Hello Thomas and viewers. So that is, so I'll just see if I can sort of illustrate that that is a point cloud, if you can see here. So that is visualizing it in 3 dimensions. I think, let me just pause for a second. Yes, I think I will let's set up nav2 and go for a drive. So I'm going to want a map here. Where is that? Okay. And I'm going to set it topic to map. And what else do we need? I think that might need to be transient, but I'm not quite sure. Okay, so we are subscribing to the map topic. Let me just going to stop the point cloud just for a second. Let's bring up nav2. I'll bring this up. And let's bring this up. That is nav2. See if we get a map. Yeah, apologies, I just had a bit of trouble getting nav2 up, so let me just try that again. Let's try bringing up nav2. I've got a video on nav2. Let's bring this up, and I've got transient local. Let's subscribe to the map. Aha. Okay, good. We have got the map up. Let's set our current position. That's what we need to do. So I'm putting us into top down. It's easier for me, and it's time for Thomas to go on the floor where he can be driven around. Okay, so we need to set up the 2D pose estimate, make sure I get that right. Okay, and I want to put some axes on so we can see where we are. We've got the axes, we're not there. That is because I have the reference frame is fixed frame. I want the robot frame. Okay, good. We're there. We have that. Bring back the point cloud. Let me just check something else. So that is the FFS2. Where did I put up my stereo pipeline? Aha, that is here. Let me just have a look and see. What did I use for that? Okay, that's from a slightly earlier camera calibration experiment. I'm going to stop this actually. I'm going to use the one that I recorded in a video a few days ago, which I think is actually better. So it was recorded on 2026 April, and the 3rd day of April. And yeah, so I've got camera calibration in that Docker volume, and I think it's better than the one I previously showed. So let's bring that up. Okay. Good. Now let me get into the, I think orbit will be a good mode. So Thomas is on the floor, and if we go round, we should be able to, so you can see that we're getting a 3D view of part of my study room, and I should be able to pick up a joystick and move the robot around, and we can then change the view. And just like I have done in previous videos, because it can be hard to show a view and drive the robot at the same time, I am going to put this whole thing into the view from the robot, and I will reset that view in, and maybe I'll use the right, is that reasonable? Maybe I'll go up a bit. I think that will work for our purposes. So if I rotate the robot, the view from the robot should be constant, and it'll be the map that changes. Let's just see if that. So there's a bit of a lag. So I think what I'd like to demonstrate is, so this is producing, this is a point cloud, and a reasonable question is how accurate is its depth estimation. So if its depth estimation is good, you would expect the point cloud to be lining up with the actual physical walls. I'm going to argue it's not perfect, but it's quite reasonable. Just for a comparison, we should, my stereo pipeline that I've just set up, we're running stereo image proc, and I'm running that because I want the rectified images, but I have got it set up so that it's also running the semi-global block matching algorithm. So it's still running that, we're not seeing it, but we can add it. So just if you look at that, we'll just do a comparison. So let's get rid of that, and there should still be a point cloud being generated by the SGBM algorithm, and that looks like that. Just to make sure it's a fair comparison, I'm going to set the point size to the same size. So that is SGBM, and if you've seen my previous video, you'll have noted it doesn't do great on low texture areas. It's got a bit of the curtain quite nicely. So I'm going to take us back to our original demo, FFS. So goodbye SGBM, and back to FFS, and you can see it handles the low texture areas. I'll just do that one more time actually. See, it's got my cupboard, and bring this back, and again it's missing some of the cupboard, and it's missing the window and the radiator. Okay, back and back here. So just to finish this off, we'll just go for a little drive around and we'll see how it performs. I think I'm going to make the argument that it is performing better than the SGBM algorithm. So there is a small lag. I haven't spent a lot of time trying to optimize all of this, but got a bit of a sort of turn around. You can see both algorithms do quite well on things like the bookcase, which is high texture, but I think this one performs better on the wall. I'll just do another of those comparison between what we got from the LiDAR and our stereo camera, so these should line up. Let me just see if I can just get that. Maybe I'll put that into, maybe orbit might be better for this. So it's not perfect. That looks like that probably should be a bit further back here. The bookcase is looking pretty good. Let me just put this back here and just okay, I think that is what I wanted to demonstrate. So you can sort of imagine potential uses for this. You could potentially use it as sort of an obstacle detector, stop it running into objects or falling downstairs. Those are my initial thoughts anyway, but I think it's quite an impressive piece of technology. Okay, well, thank you for watching.